Lovely. Thanks, Chris. Over to yourself.
Good afternoon, everyone. Firstly, thank you for inviting me along to give a presentation today at the PWI Milton Keynes seminar. The purpose of today's presentation is around updating an anachronistic track geometry standard, NRSP TRK 042, and the processes that we went through for updating the standard. And it's called 1995 because that was when that was the last time that this standard was updated. And over the past 30 odd years, it's an overview of how track geometry has evolved and why it was very important to update the standard to reflect current practices. So my name is Chris Fuller. I work in Network Rail Technical Authority as a senior engineer in track geometry. Some history about my career in the railways. I graduated in 2015 from the University of Hertfordshire studying environmental science. I mean, at the time, I was interested in going into the water industry, but I opted instead to go into the rail industry because of my general interest in railways since a young child. And I managed to land a role as an examination data technician in track geometry for asset information services. Over the upcoming 5 years, I worked my way up to become an examination data analyst and then the examination data manager of track geometry, before going over to technical authority to become a senior engineer in track geometry. At the same time, I joined the PWI and I've started my MSc at the University of Birmingham for the rail systems engineering and integration. So throughout my time working in the rail industry, I've always been involved in track geometry, particularly from the recording and delivery aspects. And when I first joined Network Rail back in 2015, I had the good fortune of meeting Ian Barber, who would later become a very good mentor for track geometry. And he taught me the three key things I needed to read about to appreciate track geometry recording. And these were the three standards which are on the right-hand side. It's NRL2 TRK 001 Module 11, which is our track geometry inspections and minimum actions. This is what the track recording vehicle report track geometry faults to, which the TME must follow. There was also TRK 038, which gave detail as to how that track geometry data should be managed in terms of how it should be processed by AIS and recorded by AIS and fed into downstream systems. And the third standard, which I was always told was the most important, was a rail track specification related to track geometry recording. And the thing that always stood out the most with regard to that standard is that Model 11 and TRK 038 were regularly updated, but TRK 042 hadn't been updated since 1995. And funnily enough, I would regularly have conversations with Mr. Barber to say what needs to be improved in this standard and what should be captured. Little would I know when I would later go over to TA, that would be one of the first things I would end up doing. So to provide some context as to what is the purpose of the standard, it's a specification which provides requirements on how we calibrate our track geometry recording vehicles and the channels which come from these vehicles so that we can have consistency among the fleet when we record our track geometry. And that's because track geometry is a paramount aspect of identifying maintenance, track safety, preventing derailments, but also to make sure that you have good ride quality. And because we have a range of track geometry recording vehicles, we needed to make sure that, or British Rail, when they introduced dynamic track geometry recording, needed to make sure that they were all within an agreed tolerance. The very earliest documentation that we have of a formalized calibration process for track geometry originated back in 1963 when the track recording Wickham Elliott vehicle was introduced by the British Transport Commission. When we moved away from a contact-based system, as shown on the top left-hand corner there of a Matisse Neptune trolley, onto an optical-based and inertial-based system, such as the track recording coach shown on the top right-hand corner, British Rail published their Handbook 38 from 1978. It wasn't until 1993 that the handbook was then updated because there had been an increase in the number of track geometry recording vehicles. And when British Rail was privatised and Railtrack came into being, the 1993 version was hastily just transferred over as a Railtrack document. And the reason why TRK 042 is important is we need consistency among our track geometry recording vehicle fleet so that when we detect a track geometry fault, we know that each vehicle will identify it within an agreed tolerance. On the screenshot here, we have on the slide here, we have a number of derailments which have been caused one way or another by track geometry. And it's through the improvement of our track geometry recording vehicles that we're able to identify faults to prevent instances like this from happening. So that's why TRK 042 is a very important standard in the world of track geometry. So if we go back to 1995 and see what situation British Rail or Railtrack was in when the track geometry recording service was contracted out to Serco Lewis, Railtrack inherited 3 track recording vehicles. On the top left-hand corner, there was the track inspection coach, which I believe was an ex-LMS inspector's saloon. And then on the top right-hand corner, there was the Mark II track recording coach introduced in 1976 for high-speed recording. And then there was also the track recording unit, which was introduced in 1987. And looking at the size of the computers and the technology which was involved, it was very of its time. It was very anachronistic, very, very clunky. But we go forwards to 2024, and we see that the track recording unit still exists, albeit in a different color. So too does the track recording coach. However, the track inspection coach was withdrawn around 2014 and was replaced by the track inspection coach 2, which later became plainline pattern recognition coach 4. But the size of the computers have shrunk, although the ability of the data and the processing that they can do has increased phenomenally. But as well as this change, we also now have more fleet. So we have the new measurement train, which was introduced around the early 2000s. In the center of the screen, we have the Frog system, which is a dynamic measurement of track geometry on the back of a SRV. We also have the multi-purpose vehicle and the class 153, which utilize unattended geometry measurement systems. So with this increase in our fleet, as well as an improved reliance upon the dynamic measurement and remote monitoring of track geometry, the integrity of TRK 042 became ever more important. However, it still relied upon processes which were agreed from 1995 and hadn't necessarily changed substantially since the handbook was published in 1978. And some of these anachronisms included the necessity for track recording vehicles to drop paint on the track if they came across a intervention or immediate action track geometry fault. On-train technicians had to be on board the train and manually sync mileposts by looking out of the window so that the positioning could be stamped on the trace. And it was also still a requirement for track geometry faults to be posted first class or second class, depending upon the severity, to track maintenance engineers. And this was a standard, as you could probably appreciate, we were not compliant to because we'd gone above and beyond those minimum requirements. So when the remit was submitted in 2022 for the specification for track geometry recording, it wasn't a simple process of just updating the standard. Track geometry and track geometry management had evolved substantially since 1995, and there were a number of stakeholders who had to be involved. This included asset information services who operated the trains, technical authority, as we're accountable for signing off vehicles and approving the annual calibration reports. Also the route end users, as we were moving into a world of unattended geometry measurement systems, what reassurances would TMEs and regional engineers and route engineers expect to see from the track recording vehicles. But I also had to liaise with suppliers to make sure that any changes we did make in the standard, suppliers were still able to meet. And on top of that layer of Network Rail standards, we also had our RSSB standards and our Working Group 28 standard from the Euronorm 13848. So we had to make sure that we were compliant to all the different layers of the standard structure. And three objectives from the remit were sourced. The first one was to update the standard to match other standards. As it was an old 1995 standard, it didn't comply to our standards and control management standard of STP 001. So there was no ragging. So we didn't know what were red clauses, what were amber clauses, and what were green clauses. The terminology was very vague. It didn't stipulate shall or should. There was many could or will inside there. Then there was also referencing that Railtrack can delegate responsibility to contractors for certain tasks, which we felt should be brought back in-house. Additionally, we had to look at what was required within, again, TRK 038 for track geometry, as well as our Euronorm standard 13848. So on top of all this, it involved us going through all the different types of standards, seeing how these had evolved, and then trying to bring TRK 042 up to scratch. The second task was to update the standard to capture existing processes. As could be imagined, since 1995, the way in which we had validated our track recording vehicle fleet had changed as well. This included details for the annual calibration of our recording vehicles, what the tolerances would be and how this information should be presented and signed off, as well as the periodic audit reports, which had to be carried out between a number of vehicles each period. And finally, for 4.3, it was to update the standard for future proofing. There's no point publishing a standard just to meet the requirements of today. I also wanted to make sure that we met the requirements for tomorrow or the next 5 years. And this included addressing issues around unattended geometry measurement systems, what should be the correct tolerances for validating our vehicles, product acceptance for new vehicles, as well as incorporating other additional checks so that we can have confidence that different systems are outputting as we would expect. So to delve into some of these in more detail, one of the first things we had to tackle with, and a task which we adopted from the Euronorm standard working group, was the definition of track geometry recording vehicles. Up until now, for a track recording vehicle to operate, there always has to be a on-train technician who is there seeing the track geometry faults as they're being recorded. So any blocked line or 36-hour faults will be called off to control and the signaler and actioned accordingly. However, there's a drive now in the industry to move away from the on-train technicians being on track recording vehicles and instead have unattended geometry measurement systems. These systems were first trialed on Network Rail around the 2010s on Virgin trains and Chiltern trains, and there's now a push to bring UGMS back. But the problem with the UGMS recording vehicle fleet is we can't take these vehicles out of revenue service to take them to a approved test track to validate their recording output just because of the disruption and restrictions. So we had to differentiate between track recording vehicles which were effectively Network Rail owned and maintained against track recording platforms which were operated by train operating companies. And in this, we adopted the use of a primary track recording system and a secondary track recording system, whereby we have a dedicated vehicle with fixed measurement systems on board, which is validated at an approved calibration site and has to be validated against other track recording vehicles at the same time to confirm consistency. whilst a secondary track geometry recording system will undergo what's known as a virtual test track, whereby it runs over a section of track, let's say on the East Coast Main Line, which we've run one of our primary track geometry recording systems over, and then we effectively use the primary system as a datum to validate the secondary system. And this was quite a challenge for us to try and see how best we could introduce this and govern this. But this is the way in which we approached that first challenge. Other things came around the repeatability tolerances, the reproducibility tolerances, and the comparability tolerances. So for track geometry systems to be validated, they have to undergo repeatability, reproducibility, and comparability. It's slightly difficult to explain this on a slide, but hopefully this will detail it. The purpose of a repeatability test is that the same track recording vehicle would go over the same section of track in the same orientation at the same speed on the same day. We run that multiple times, and we would expect to see similarities in the data output, plus minus whatever's listed in table 3. This tells us that there was repeatability in the system, and there isn't randomness, which is throwing out, let's say, track twist greater than 1 millimeter. So repeatability, although it's not mandated for all the track recording vehicles all the time, it is a very good reassurance to check that the same piece of kit is producing the same results as we would expect. The next part was the reproducibility tolerances. This is to run a track recording vehicle over the same section of track on the same day, but at different velocities and in different orientations. And the reason why we will do this is to make sure that if the vehicle was in a reverse formation, we would still get the same results if it was traveling in a forward formation. And we also want to make sure that as the vehicle's velocity increases, it doesn't impact the output of the track geometry channel. This is a very tried and tested method which originates from the days of British Rail. And what we wanted to do was just specify by tightening the tolerances, particularly for twist and gauge, because these two are major contributors to derailments and are normally the main area of complaint when we speak to track maintenance engineers about potential inconsistency among the fleet. So we tighten the tolerances from 2 millimeters for twist and 2 millimeters for gauge to 1.5 millimeters for both. And in doing so with the reproducibility, we were able to just demonstrate an improved accuracy and precision that the vehicles are able to output. And the third test that we conduct is a comparability test. A comparability test is, I would argue, one of the most important tests that we have to conduct of our track recording vehicle fleet. So after a vehicle's had its reproducibility and its repeatability test, we next want to make sure that all the vehicles are within tolerance of each other. And the comparability will mean that you would have train A, train B, and train C running on the same section of track in different orientations and different velocities. And from that, we would expect to see an agreement based upon the tolerances shown in the table of about 95%. Comparability is very commonly used for our periodic audit reports because we have sections of track around Derby, which are audit sites which the track recording vehicles operate over. And from this, we're able to retrieve the data and run statistical analysis on the comparability. But we also found an opportunity to use comparability to validate our unattended geometry measurement systems or our secondary recording systems, as demonstrated on the graph on the bottom left-hand corner. Where we have 3 track recording vehicles highlighted or colored in yellow, these have been confirmed as valid on a approved network rail test track. Then what we will do is take one of these vehicles or 2 of these vehicles, run them on an approved virtual test track, and have the UGMS system on a TOC train running on the same section of track. So what we would then expect is that the UGMS system on vehicle A should match with our primary track geometry recording system C and B. Then that way we're able to have consistency among the fleet. And this has proven to be quite effective at the moment when we're running through the process of signing off UGMS on our train operating company fleet. Another thing I pushed to add into the standard, and the working group endorsed it, was an additional check, which we call actual fault or pseudo fault count. Statistically, a vehicle over 5 miles may be plus minus, maybe within 95% of the plus minus 2 millimeter. But one of the main issues of complaint we often received from the track maintenance community was consistency among the fleet. And this would often have an impact on the output of track geometry faults. And we report these track geometry faults to the ORR. So we need to make sure that these instruments are demonstrating a reliable output. And using the example shown on the left-hand side there, we have track recording vehicle A and then track recording vehicle B. Both of them have travelled over the same section of track, and we can see that one of the vehicles has produced 2 faults, a positive twist and a negative twist, whilst track recording vehicle B has only produced 1 fault of a level 2 fault of negative twist. But when we look at the peak of the track recording vehicle A at 15.1 millimeter against track recording vehicle B of 14.9 millimeter, although that 14.9 is just below the 15 millimeter tolerance to become a valid track geometry fault, it is still within the plus minus 1.5 millimeter tolerance for comparability in table 5. And the idea of doing this is that we can understand, when we do receive concerns from the routes and regions, that we can demonstrate that the vehicles are within tolerance, but it's because they're recording on that threshold into what makes a track geometry fault. We've also called it pseudo fault count because we tend to validate our track geometry recording vehicles on Old Dalby Test Track or Tuxford. The track quality at these sites is phenomenally very good because these don't undergo the normal daily tonnage and traction and traffic that you would expect to see on a conventional main line. So it may be when the track recording vehicle runs over the site, none of them produce any track geometry faults, but they may be picking up plus 10 millimeter, plus 11 millimeter features on the trace. So what we can do with a pseudo fault is we can look at anything above 10 millimeters and see how that compares against another track recording vehicle to see if it's still picking up within the plus minus 1.5 millimeter. So from this working group and from looking at other standards, from liaising with our suppliers, other departments within Network Rail, the wider industry, both within the UK and in Europe, we were finally able to update NRL2 TRK 042 after 29 years. And that's a long way from when the standards were first introduced in 1963, all the way through to 78, to 93, and to 1995. But the important thing is, now that the standard has been published, it isn't going to end there. One of the benefits of conversations we had in the working group is that we have aspirations to further tighten the standard, to introduce additional checks to confirm that our track recording vehicles are continuing to be accurate. And so we have a post-implementation review meeting in December this year, and I've been conducting a little bit of research myself to see whether we should be using datum track, such as slab track, as a way of validating our track recording vehicles. One of the problems we have of the comparability or the repeatability or reproducibility of our track recording vehicles is they may all be within tolerance, but they are all within tolerance of each other. What we don't necessarily know is what is the gauge at that location that they were tested on, or what was the actual value of a track geometry twist fault there. And using the scenario at the bottom left-hand corner, if we were to stick with plus minus 2 millimeter tolerance for gauge, PLPR1 could be measuring a section of track at 1441 millimeters, whilst NMT could be detecting it at 1440 millimeters. Technically, those two vehicles would pass each other, because they're both within ±2 mm. But if the track was actually 1435 mm, then in theory, those two vehicles would fail because they're outside of 2 mm of 1435. There's actually a 5 mm difference. And this follows on to an investigation that occurred a few years ago on the East Coast Main Line, where we were receiving reports that one of the vehicles was reporting tight gauge, whilst another vehicle was not detecting this tight gauge when it was going over the same site. So colleagues on Eastern measured the slab track through Gasworks Tunnel, and I was able to annotate the data and then demonstrate that the new measurement train was reporting track tighter to the slab track by -1.14 mm. This then allowed us to go back to Asset Information Services and tell them they needed to adjust the optical system on the NMT and bring it into compliance with the slab track and PLPR1. But this is a major task because we know slab track can degrade over time, and there needs to be that confidence that when designing a datum and using a datum, that the datum itself is accurate, or else we could end up in a situation whereby we've actually confused all the track recording vehicles. So this is what the working group for TRK 042 has done, and it's been a tremendous achievement to update the standard. It was a very long and tiring task, primarily because of the way in which the industry had changed and the varying degrees of opinion as to how we should best retain the integrity of our track recording vehicle fleet. So it's something I wanted to share with the PWI, because it's a very important standard. It's a paramount standard, I would say, for having reassurances in our track geometry. And it's a great achievement that the TRK 042 working group was able to update this standard, and it's been a pleasure to do that. So I just want to say that over the past 29 years, many things might have changed, but in terms of our track recording vehicles, with exception to the hardware and the software, most cases the only change people would see would be the color. So thank you very much for the listening to the presentation. I open the floor to any questions.
Brilliant, thanks, Chris. That was great. Jaden's got first question, I think. Put his hand up. Go ahead, Jaden.
Yes, a question for me. Thank you for that presentation, Chris. I can't imagine it was actually very easy to update a standard. It's basically almost from another time period. It's from the 1900s, you could even say. Like, I imagine some of the requirements in that standard were vastly outdated by the technology. I don't imagine it was just the delivery by mail that you were mentioning. And essentially, they've been outstripped by technology that's probably been around for years. What advice would you give to someone else who had to deal with such a vast update? Because I imagine when you were doing that, there were some clauses in that standard you just had to completely tear away in order to rewrite.
Yes, because the suppliers of track geometry in 1995 were Serco Lewis, and Serco Lewis was just the British rail system privatized. The man behind a lot of it was Raymond Lewis, and then he went over to Serco and then just took his knowledge and the technology over with him. So we knew from the days of Serco Lewis, which was last used in 2014, and our current system, the TrueTrack system from Omnicom Balfour Beatty, which was introduced in Ango around the same time, 2013, that not only had the software and the hardware changed, but also the precision or accuracy of the systems have changed as well. So from that respect, I had to get the suppliers on board, because we knew as an industry what we wanted the track recording vehicles to measure to. We knew what we wanted for their accuracy and their precision, but we also knew the limitations because of optical-based systems, because of changes in technology. So as part of this, I had conversations with our main supplier, Omnicom Balfour Beatty, to say that this is what we have, this is what we used to do in TRK 042, but this is what, from my perspective as a technical expert, I know can be done. If we were to put that what can be done in writing, would that have an impact on OBB? And they were very cooperative, and they said that we could actually go tighter. And so we had very good conversations with them. Another aspect was with asset information services, who are the ones who have to produce the reports and then also record and do the calibration runs. We had to make sure that if we were to say this is what we want to do, this is the methodology, what is the financial impact, what are the resource impacts? Some of us were very keen that we wanted to, for example, increase the annual calibration to maybe having it twice a year. But AIS turned around and said they couldn't accommodate that just because of the sheer costs and the disruption of taking vehicles out of the yearly plan just to calibrate them. So those are areas where we've had to compromise. So yeah, it was a mammoth task, but getting everyone together in the same room and just going through the standard and saying this is what we know we don't do, but has that been superseded, or is it a case we don't do it anymore? Cross it off or write down what we do instead, and then review the standard with key stakeholders.
Thank you for that, Chris.
That's all right.
Thanks, Jaden. Anybody else got any questions? There's none in the chat that I can see. I'll shout for any questions. Okay, yeah, that was great, Chris. That was really enlightening. I thought the item around the UGMS calibration was really insightful. How that's done. I always thought how on earth did we get that to be so good? And I thought, yeah, we should be tightening up on tolerances, like you mentioned towards the end of your presentation. I think using slab track is a great idea, isn't it, to sort that out? But as you say, some of the balance between the technology and what we can do in repeatability and calibration. Yeah, really texting field. So thank you very much. So yeah, if everybody could join me in thanking Chris in the usual way, or with the hands up. Thanks, Chris.
That's all right.
I think we fought against a nice, really hot summer or start of the summer day. I think that's what we're